Hello, I'm Brian Young, and today we're going to do 26202, Motors, Theory and Application. Let's get started. 26202, Theory and Application of Motors. Successful completion of this module prepares you to do the following: identify direct current motors and describe their operating characteristics. Describe how DC motors operate and identify types of DC motors. And I'll read the rest when we get to sections 2, 3, 4. Under supervision, you should be able to identify various types of motors and their applications, collect data from a motor nameplate, and connect the terminals of a dual voltage AC motor. The electric motor is a workhorse of modern industry. Its functions are almost unlimited in scope. To power and control motors, we need compatible electrical power circuits with certain characteristics. They must provide electrical current that causes the motor to operate as needed so it performs its intended function. Motors described, this module describes the construction and characteristics of both alternating current and direct current motors, enabling the electrician to better understand the power and control requirements. Motor operation. Compatible electrical power circuits with specific characteristics are used to power and control motors. These characteristics include providing electrical current and protection from adverse mechanical and electrical conditions. These functions are often combined within electrical equipment known as motor control centers, MCCs. You'll hear that on bigger jobs. Thorough understanding of motor control centers is important for both a maintenance and troubleshooting perspective. Properly maintained motor control centers serve to minimize downtime for unscheduled repairs, increase productivity, and contribute to a safer work environment. So, how DC motors operate. Basically, it's two magnetic fields that are opposing each other. It says when a bar of magnetic material is given an induced magnetic charge, a field of magnetic force is developed around the bar. Picture this field as consisting of magnetic lines of force or flux that exist in the space surrounding the bar. These lines of force appear to leave one end of the bar and extend outside the bar to the opposite end. If you've ever seen an example where somebody takes a piece of paper and puts it on a magnet, and then they drop iron filings on it, all of the iron filings line up in these radial bands running. They say, and I take the scientists at their word because they're smarter than I am, that the lines of flux leave the North Pole and enter the South Pole. So lines of magnetic flux always travel from north to south. And we're just going to take that as a given and not try to disprove it. There are several characteristics of these magnetic lines of force that must be remembered when dealing with electric motors. Magnetic lines of force are continuous and always form closed loops. Magnetic lines of force do not cross. That's an important characteristic that we have to keep in mind. Magnetic lines of force do not cross. Magnetic lines of force with polarities in the same direction repel each other. In other words, a North Pole repel a North Pole, and a South Pole will repel a South Pole. Magnetic lines of force with polarities in opposite directions tend to attract each other. In other words, the South Pole will be attracted to a North Pole and vice versa. Magnetic lines of force tend to shorten themselves. Therefore, the magnetic lines of force existing between two unlike poles cause the poles to pull together. Magnetic lines of force pass through all known materials, magnetic or non-magnetic. Some materials provide a much easier path for these lines than others. So, direct current motors consist of a few major components, each of which with a specific purpose in the motor's operation. The armature is a movable electromagnet located between the poles of another fixed permanent field magnet as shown. So They call these the field magnets, and this is the armature magnet. And if we let go of this magnet, it's going to spin until the north is attracted to the south and the south pole is attracted to the north. And that's where this is going to stay and remain there. So if there's some way of disconnecting this magnetic field and reversing it when it gets to this horizontal position, if we can change that north to a south, it will be repelled by this south pole and attracted to this north pole. And when it gets to here, if we can change it again to a north pole, it will be repelled by this north pole and attracted by this south pole. And that's how a DC motor works. We continuously change the polarity of the armature. So here are lines of flux running from north to south, and you can see that there is a conductor being pushed through these lines of flux. And what happens is it distorts these lines of flux. They bend, they go around the magnetic lines of flux that are running around that conductor. So it's causing, this current is coming toward us. This current is going away from us. So as the current goes away from us and it creates these lines of magnetic flux around the conductor, it will push this conductor through this magnetic field with the lines of flux going from north to south. And again, in doing so, it distorts these lines of magnetic flux. It says unless the two fields are the same plane, they cannot affect each other. In the same plane, however, lines of force in the same direction reinforce or to make a stronger field, while lines in opposite directions cancel and result in a weaker field. The stronger field tends to push the conductor toward the weaker field. So, in other words, when these lines of flux are going from north to south, and these are also going in the direction of those arrows, these two aid each other and it pushes this conductor up. This is weaker when it's opposing the north-south field. So it draws it up. It actually pushes it up through that, the permanent magnets. In motor action, the wire moves only in a straight line. The wire stops moving when outside of the field, even though current still exists. A practical motor must exhibit continuous rotary motion, and to produce this, a twisting force called torque must be developed. So what they do is they take a loop of wire and they put it on an axis, and then that loop of wire can turn freely inside of this north-south field magnets, field windings. So they're showing a commutator. This commutator, did they mention the commutator? There we go. To get continuous rotation, the armature must be kept moving in the same direction. This requires reversing the direction of current flow through the armature every 180 degrees of revolution. A commutator is used to provide this switching action. So a commutator is a switch. It's a switch that turns on and off this magnetic field. For half the rotation, this is a south pole and it is repelled by the south magnet. It spins over, and just before it gets in line with the north magnet, just before it gets to 180 degrees, this commutator turns off and turns it back on in the opposite polarity. At this break, it loses contact with the brush, and then the other commutating section will come in contact with the brush, and it will change the polarity of the current flowing through this armature, through this coil of wire. So when the coil of wire that was a south pole comes over to here, all of a sudden it becomes a north pole, and now it's repelled by the north magnet, and it's attracted to the south magnet. And when it gets right over to here, it changes polarity again and becomes a south pole. And you can do this. You can do if you have a compass and two permanent magnets, you can do this. It's hard for me to show you. I've got my camera set up and I don't really change it, but here we go. Let's see if I can show you this here. So if you do have a compass, here's your compass. This is something you can do at home, or you can do it in class. Here's the North Pole, and I'm just going to draw like that. Maybe I can rotate that. Then we're going to take two magnets. I'll take actually, I'm going to take two north magnets. I know that sounds ridiculous, but I'm going to take two north magnets instead of a north and a south. And what happens is the north pole of this compass is going to be repelled by this magnet. I'm only going to set one magnet down at a time. So I'll set this magnet down, and it's going to, oh, come on. There. It's going to repel this needle until it gets over here. And when it gets over here, I'm going to lift this magnet up, and I'm going to set this magnet down, and it's going to repel the North Pole. When it gets over here, I'm going to set this magnet down and pick this one up. And you can do that. You can take those two magnets and you can drum it on either side of that compass. And if you get just the right rhythm, you can make this needle on the compass spin. And that's a motor. That's how motors work. We're going to continue changing the North Pole, which side it's on. And yes, what they do is they have a north and a south, and instead of changing these magnets, they change the magnetic poles of the armature. Well, we can't do that with a compass. It's permanently north on the red tip. So we will just change these by drumming them. You put down this north and you put down this north, and it's a pretty fast beat. If you're in a class, that's a good competition for you all to try to see who can make it the steadiest, who can make it the fastest, who can make it reverse direction. If you do it just right, you can do all three of those. All right. Let's see here. Where am I? Let's go back. So, the commutator is used to provide this switching action. It changes it. Commutator on a DC motor is a conducting ring that's split into two segments or more, with each segment connected to the end of an armature loop. Current enters the side of the armature closest to the south pole of the field and leaves the side closest to the north pole of the field. The interaction of the two fields produces torque, and the armature rotates in that direction. Now, a brush makes contact with each segment of the commutator as it turns, providing a connection between the movable commutator and the stationary DC power source. Figure 6 shows various brushes. So these carbon brushes are making contact with the commutator as it turns. And as it's rotating, it's connecting an electrical current to different parts of the commutator and different windings in the DC motor. And you can see from the number of commutator segments that there are a lot of different windings in this DC motor. So it's going to have a very smooth operation. It's going to spin really nice. And it's kind of interesting that they have two connected at one time, because that gives us a wider field in our armature. It actually causes the armature to spin in only one direction, so you don't have it accidentally start up and go in the opposite direction. Problem of switching commutator segments in a simple single loop motor is that when the motor stops, there's no way of predicting the position of the armature at rest. If the armature stops in a position where the commutator is in the middle of switching, the motor will not start unless you physically turn the armature. This problem can be overcome by winding more coils on the armature and by using more commutator segments. This will produce a self-starting motor. So that's what they're doing here. This is a self-starter motor. This one has 3 coils, and at any given moment, one of these coils is going to be making contact. So you'll get current flow, and then you'll have a north and a south, and it'll cause this to turn. The brushless DC motor was developed to eliminate commutator problems in missiles and spacecraft operating above the Earth's atmosphere. So, two general types of brushless motors are in use: the inverter induction motor and a DC motor with an electronic commutator. These brushes made of carbon will create carbon dust. So they came up with a brushless DC motor so that they don't have that problem. You don't want dust out in space. It's going to cause problems. So it's a nice, clean, brushless motor. The neutral plane. Let me discuss the neutral plane. Come on, there we go. So basically the neutral plane, if I have a North Pole and I have a South Pole. It's terrible. And I have lines of flux moving from north to south. The neutral plane is that point where there's zero induced voltage on the armature. So here at 0 degrees, that is where our neutral plane would be. However, as you rotate this armature or this coil of wire inside of this magnetic flux, it has a tendency to change. Well, they're doing theirs counterclockwise, so let me go counterclockwise too so I don't confuse the issue. As this armature is spinning inside of these lines of flux, they distort the lines of flux. They distort them. The lines of flux do not cross, so they have to move to get out of the way. And what happens when they get out of the way of the spinning armature is they do something like that. I'm not going to make them, well, okay, there, I'll make them dotted. They come out looking something like this. Well, gee whiz, that's terrible. Hold on, let me get rid of all of these. I wish I could just get rid of one color at a time. That would be convenient. But we're going to take all of these, and I'm just going to draw solid lines just because it's a little easier. But these lines of flux end up looking like this. You can almost imagine if you had a paddle wheel in a lake, that the paddle wheel would distort the surface of the water as it spins. It's going to cause one side to be lower and one side to be higher. And that's what happens in this neutral plane. All of a sudden, the neutral plane shifts. It gets shifted, and I'm going to say 17 degrees. I don't know why. I heard 17 degrees once as a student, and it's just always stuck with me. But I'm going to say it shifts about 17 degrees. Now that I'm saying that, I think that's wrong. I think it's 7.5 degrees. Anyway, it's going to shift. It's going to shift in the direction of rotation. So your neutral plane is no longer 90 degrees, or it's no longer perpendicular to your north and south magnet. So you have to also make your commutator shift that same number of degrees. You don't want arcing at your commutator, and if you're connecting and disconnecting power while that power is active, then you're going to get sparking. If you can wait till the power drops to 0, and that's at the neutral plane, if you can wait till it drops to 0, then you can disconnect that power and have minimal arcing and sparking. So that's what they're going to do. They're going to change the position of the commutator in order to try to mitigate the effects of that arcing and sparking. And you can see this yourself if you have a drill motor. It can be a battery drill. It can be the best ones are the corded ones. You plug it in. Go into a dark room and plug in that drill motor and squeeze the trigger. You're going to see the 4th of July down inside that drill motor. It's where the commutator pieces are turning on and off from the electrical power. When it switches, it draws an arc every time. So it says when the loop reaches a position perpendicular to the field, the interaction of the magnetic field stops. This is the neutral plane, that point where the interaction of the magnetic fields stop. But as we turn this, and I'm not going to read all of this, I'm just going to show you. There's your torque. Torque is a circular force. Whenever they use the word torque, they mean circular force. So here we are rotating this armature inside of this magnetic field. Well, where did you show me that? You're supposed to show me that. There you go. What happens is it bends these lines of magnetic flux and it changes our neutral plane, shifting the neutral plane due to armature reaction. There's the theoretical axis of the neutral plane. This is the actual axis. And now I've confused myself. I can't remember if it was 7.5 or 17, but it was too many. It was 100 years ago. When a motor armature is supplied with current, a magnetic flux is built up around the conductor of the armature windings. Armature reaction is caused by two magnetic fields, the main magnetic field from the field magnets and the magnetic field produced by the armature. These two fields combine to produce a new resultant magnetic field. The resultant field is distorted and shifts opposite the main field and opposite the direction of armature rotation. This distortion shifts the neutral plane of the motor. So it shifts that neutral plane. The amount of armature reaction determines how far the neutral plane is shifted. The amount of armature reaction depends on the amount and the direction of the armature current. So this armature reaction can be overcome by installing interpole windings. Interpole windings are special electromagnetic poles that are connected in series with the armature winding. The armature current causes a magnetic field to form around the windings. Their action is self-regulating, and the interpole field will apply the proper amount of cancellation field for any set of conditions. So these interpole windings cancel out the distortion of the lines of magnetic flux, and they bring that neutral plane back to center between the north and south. Interpole windings. Counter electromotive force. Well, okay. To understand counter electromotive force, first disregard the fact that the external current is being applied to the rotor via carbon brushes on the commutator thing. Basically, for me to explain counter electromotive force, I have to tell you that motors, generators are cousins. If I had the pieces of a motor on my desk and I showed you and I said, this is a motor. Here's the rotor, the part that rotates. And here's the stator, the part that is stationary. That's the field windings. The field windings in an AC motor are called a stator. They don't rotate. And the armature is called the rotor. It rotates. So you have a rotor and a stator. The rotor rotates, the stator is stationary. And then they're held in place by a core. So I could hold up the core and I could hold up the armature, or the rotor, and I could show you the stator windings inside the core. If I then had a generator and I took it apart and showed you, they look identical. They look just the same. They're cousins. Every motor acts like a generator. So as you rotate a coil of wire in a magnetic field, you induce a voltage and a current in that coil of wire. So a motor is doing just that. The power driving the motor creates a magnetic field that causes that rotor to rotate inside of the magnetic field. But because it's a coil of wire rotating in a magnetic field, it's generating a voltage of its own. And that voltage is 180 degrees out of phase with the voltage that's driving it in the first place. That's why they call it counter electromotive force. That's a good thing, because if it were additive, if it induced a voltage and a current in the same direction as the supply voltage, it would be additive and the motor would race away. It would continue to gain speed until it self-destructs. The centrifugal force would literally throw the windings out from the rotor. It would self-destruct. So it's a good thing that we have counter electromotive force. So electromotive force is another word for voltage. It may also be referred to as electrical pressure or difference of potential. That's actually a good thing to know. I don't know that it's going to be on the test, but I'm going to highlight it because it's a good thing to know. Before analyzing the relative direction between the current induced in the armature winding and the current that causes the field poles, first remember the left-hand rule. So give me a moment. I'm going to have to draw the left-hand rule, so I'm going to take a little quick break. I'll meet you back here in a minute. Okay, so here's my left-hand rule. It's not my left-hand rule. This is the left-hand rule. So the thumb is the thrust. That's the motion of the conductor, the direction the conductor is moving. And the forefinger is flux. That's the magnetic flux flowing in the circuit. The direction of the magnetic flux. So the thumb is thrust. Well, these aren't going to line up, but that's okay. Basically, what we're making is the XYZ axis. And then the middle finger is motive force, and basically that is the current flow in the conductor. Okay, so thumb is thrust. I'll have to do it with the other hand because I'm a mirror image. I can't do it. Can't turn around. Anyway, let's see, is that right? No, that's opposite. This is a mirror image. I can't do it. All right, your thumb is the thrust. That's the direction that the conductor is moving. The forefinger is flux, and the middle finger is the motive force. So when I have battery piece, well, when I have magnets, here's a north, and here's a south. Basically, the lines of magnetic flux are moving from north to south. There. And if you take a conductor, I'm going to draw this conductor in two different ways. I'm going to draw one with a dot, and that's the head of an arrow, and I'm going to draw it with plus, and that's the feathers on the arrow. So those are the feathers. So when I draw a plus, it means that the current is going into the board. When I draw a dot, that means it's coming out from the board. Okay, so I need to take this and this and tie them together. There you go. So when we're talking about a generator, when we're up here at 0 degrees, we're not inducing a voltage or a current in this wire. But as we bring this wire down through these lines of flux, we increasingly induce a voltage in this conductor. And we induce it in such a way that on this half, the induced voltage is of such of a polarity that causes the current to go into the board. And we would have to, let's see here, how do I do this? I want to try to, okay. So if I can put my hand here, there. So there's four-finger flux. That's the direction of the lines of magnetic flux. And my thumb is pointing in the direction of the movement of the conductor through the magnetic flux. It's going from the top to the bottom. And this middle finger is pointing into the board. It's pointing into the board. So when it's coming down, the current is actually going into the board. So I've got to actually draw it wrong here. So what I need to do is change my drawing. So at this point, come here, you. There. Let me make myself small again. Where am I? Let's get small. All right. You guys don't remember Steve Martin. Let's get small. All right. So here's my plus crosshairs. So while this while this is going down the right side of the lines of flux, the current is going into the board. And then it gets down to the neutral plane where things switch. And as this conductor comes up the other side, guess what happens? It's actually coming out of the board because of that left-hand rule. So now, let me get this guy out of here so I don't erase the wrong thing. So now, all of a sudden, I have there. Now it's coming out of the board. Just a second ago, the current was going into the board. Now it's coming out of the board because it's going through these lines of magnetic flux in such a way that the thumb is the thrust and the forefingers the flux, and the middle finger is the motive force. It's the electrical current coming out of the board. So down this side, it goes into the board. Up this side, it comes out of the board. It goes into the board, it comes out of the board. It goes into the board, it comes out of the board. But in explaining that, what we're saying is that the motor is acting like a generator. It's actually generating its own separate voltage and current, and it's 180 degrees out of phase with the driving voltage, so it's counter electromotive force. Using your left hand, hold your index finger points in the direction of the magnetic field, the flux, and your thumb points in the direction of the rotational force on a given conductor, the thrust. Your middle finger will now point in the direction of current flow, the motive force for that conductor. When first discussing counter electromotive force, we disregard the fact that DC was being applied to the armature via the brushes. It says this was an oversimplification because only one current flows, because the counter electromotive force can never become as large as the externally applied voltage. Ooh, there you go. Because the counter electromotive force can never become as large as the externally applied voltage, and because they are opposite in polarity, the counter electromotive force works to cancel only a part of the applied voltage. the single current that flows is smaller because of the counter electromotive force. Well, sorry, I gotta go back to my 3D BB here. I've gotta show you this. So you've got a motor, and when that motor first starts, let's see, where's the black there? I'm gonna graph the current. At startup, as soon as we start this motor, there's nothing opposing the flow of current except the resistance of the armature. So a lot of current flows, sometimes as much as 5 to 7 times the running current of that motor. So if you have a motor that runs on 35 amps or 30 amps, you could have as much as 210 amps flowing at startup. But very quickly, as the armature starts to rotate, that motor starts generating a counter electromotive force, and that counter electromotive force opposes the source voltage, and it brings that running current down to its 30 amps. So it's a good thing. We might start at 210 amps way up here, and then as it comes up to running speed, it levels off at the running speed, the full load current of 30 amps on that motor. So when we talk about overcurrent protection for a motor, we're going to sometimes go as large as 250% of the running current of that motor. In some instances, we'll go 300% of the running current of that motor in order to provide for startup. We also want to use the circuit breakers that are not instantaneous trip. We want to use the inverse time relationship, meaning if it has 5 times the rating of that circuit breaker, if it's a 50 amp circuit breaker, and we go 5 times that 50 amps, it won't trip for 30 seconds. It'll allow 5 times the running of the current rating of the breaker to last for 30 seconds. If we put 5,000 amps on it, it'll trip right away. It's an inverse time relationship. The higher the fault current, the faster that circuit breaker will trip. So that's what we use for starting motors. We need something that's going to allow an overcurrent for 2 seconds, 3 seconds. And then we get down to the running current, and it didn't hurt the windings, it didn't hurt the supply wires, it didn't hurt the circuit breaker. Everybody's happy, but it allowed it to do that. If we had an instantaneous trip circuit breaker of 200 amps, it would probably trip as soon as we tried to start the motor. So, all right, let's go back. So, because the counter electromotive force of a motor is generated by the armature windings cutting the lines of force set up by the field poles, its value will depend on the field strength and the armature speed. Now, all right, I'm not going to get into the semantics here. Study that. If you have any trouble, just ask me. But I'm not going to get deep in the woods here with a lot of math. Resulting reaction when no counter electromotive force is produced, that's called locked rotor. If you have a locked rotor, if there's here they've got a branch or a stick or something keeping this from running, this is going to very quickly overheat, and it's going to burn up the windings of the motor. So you have to have a motor starter that has overload protection, and it'll trip and it'll disconnect the power to that motor to allow you to know there's something wrong. Large DC motors require that starting resistance be inserted in series with the motor armature. The current drawn by the armature is governed by the counter electromotive force and the armature resistance. When starting, counter electromotive force will be 0 because the rotor is at a standstill. There's also no inductive reactance as in alternating current induction motors. This means that the starting current will be abnormally high unless limited by an external starting resistance. So that's what they'll do. They'll put a resistor in series with the armature, and they can shunt it. They can disconnect that later on, that resistance. There again, they get into math here where they're saying that total voltage minus the counter electromotive force divided by the resistance of the armature gives you the current on startup. So we need to limit that. We can't let it be. So we want to try to limit this to 36 amps. And here they have a formula where you take the total voltage, 250 volts, minus the counter electromotive force, and at startup that's 0, minus the current, which we want it to be 36 amps, times the armature resistance, 0.5 ohms. And you divide the whole thing by 36 amps. And if you do this in your calculator, you come up with 6.44 ohms. So basically they're saying if we put a 6.44 ohm resistor in series with the armature, we will protect that armature from overheating. And as it speeds up, as we start inducing a counter electromotive force, we can then remove that resistance. We can have a centrifugal switch that at 70 or 80%, it's going to bypass that resistor. It'll just put a jumper across it. It'll short it, so no current is going through it. And then there's also, they can find what the wattage needs to be. Anyway, all right. Horsepower is 746. 746 watts equals 1 horsepower. So you take the watts and divide by 746, and it'll tell you the horsepower of that motor. All right. DC motor types. We have shunt and we have series. All right. I've been talking too long. I'm going to go ahead and start another video. So I'll see you on part 2.